we will have our lecture 2. This is about a review of the CMOS scaling. And we also will talk about the industry trend. So this is not necessarily related to the memory technologies, but in general, including the logic, we want to have a better understanding of the CMOS technology and also the industry. So we will have a brief review of the Mosfet, and then we will talk about the scaling challenges and solutions for the CMOS scaling. And then finally, we will cover the industry landscape. So here, I assume that all of you understand the MOSFET structure, right? So this is for the planar MOSFET. And then we have the source and drain. And then from the layout point of view, then the key dimensions is the channel width and then the channel length. Okay, the W over L defines the current drivability of the transistor. So I'll quickly go over this. I assume this is some fundamentals that all of you are familiar with. And then the CMOS technology really require NMOS and PMOS co-located, because for many of those Boolean logic operation, you need NMOS and PMOS, right? So here you can co-locate NMOS and PMOS, but for PMOS, you may need to pre-fabricate an N-wheel. So here, this forms the CMOS technology, right? The basic circuit inverter, is made of one NMOS and one PMOS. So if you look at the MOSFET device physics, what is important is to understand the band diagram, especially from the 3D view like this. So here, if you look at the band diagram from the source to the drain, in the 3D view, here we have to lay down the transistor by 90 degrees to be aligned with this kind of 3D view. But anyway, so here the source and the drain, and then PN junction, right? So then the gate has the higher energy potential. So this is for NMOS, okay? When the gate voltage is 0, then source and drain, you have a lot of electrons, and they are separated by the channel region, which has higher potential. There's a barrier here. And then when you apply the gate voltage, what you do is near the surface of the silicon, you bend down the band because the positive gate voltage will push down the band. So here the barrier height from the source to the channel is lowered. So that's why you have the current or electron flow. And then if you apply drain voltage, so here you will have electrons in the channel, like channel inversion, but you will not have flow of the current because they are equal potential, right? Source and drain. So now if you apply drain voltage, then you will push the drain band down. Then you have this slope. So the electrons are like water, they go to lower potential. So that's why you have the current flow this way. So this is how you understand the MOSFET operation from the band diagram's point of view. So this band diagram will help you to understand many other phenomena like short channel effects and then band-to-band tunneling and so on. So we will quickly review the IV characteristics. I assume you understand those. Okay, here we have two representative IV plots. One is IDVD. This is also called the output characteristics of the transistor. You have a question?
Yes. The previous diagram, the 3D shape, it seemed like it was only bending on one side. Is there a reason for that? Wouldn't the gate voltage be applied uniformly across?
So here, if you do not apply drain voltage, yes, then here the bending will be uniform across the channel. But here, when you apply drain voltage, right, the drain side will be pushed down further. So that's why you have the slope. Yeah, gradient. And the other one here is the transfer curve. Okay, transfer curve, that is IDVG. Okay, and then here you have different curves because in the IDVD you ramp up the gate voltage, then you will get a group of curves like this. And then here there are some like key parameters, for example, threshold voltage, and also here the saturation voltage, which defines the linear region or the triode region versus the saturation region. But in the practical transistor, you know, the saturation never saturates due to the short channel effect and channel modulation effects. So here, then even in the saturation, the drain current will further increase a little bit. So here are some more, you know, definitions on some of those parameters. For example, the resistance of the channel is defined in the linear region, which is the slope here. This is because at the linear region, the transistor is more like a resistor, right? The transistor could be approximate as a resistor in the linear region. So this resistance is given by the inverse of this slope. And then the output resistance, this is more like a small signal concept, which is the slope here in the saturation region. Then you have the small signal output resistance, or in many cases, like a small RO. This is important for analog circuits, like the amplifier. The intrinsic gain will be GM times RO, your transconductance times RO. So if you have a small signal here, then it will amplify, right, the signal depending on the slope. And then here's on current, which is when the VGS equals to VDS equals to VDD, the power supply voltage, then that's the maximum current you can get from this transistor. That is the on current, and is normalized to the width of the transistor. Typically, let's say 1 micrometer wide, how much current, milliamp current, you may get from the transistor. And then the transconductance is a gradient, let's say the delta ID over delta VG. So by varying the gate voltage, how much drain current change you may get. This is defined as the GM, transconductance, which is also important for the analog circuit design. So those are just some basic stuff. I assume you learned that through your undergrad study already. So let me spend a few more words on the subthreshold slope. Okay. So this is a IDVG plot, but in the semi-log scale. That means the drain current is plotted in the log scale. This is how it looks like, okay? So here, this is like a threshold voltage. And below that, this is like a subthreshold. There's still current flow below the threshold voltage, but then the current will exponentially decay when you reduce the voltage from the threshold voltage down to 0. And then here, the slope, okay, is defined as the subthreshold slope S, or sometimes we call SS. It has a unit like a millivolt per decade. Decade means you reduce the current by 1 order of magnitude, 10 times. How many millivolts you need to reduce? So this is a very important characteristic. A good design needs to make this steeper, the better. Okay. So here, mathematically, you have this formula, which is defined as S is defined as the derivative of the log ID over VG, and then using the chain rule of the calculus, you can divide this into 2 parts. So here, the partial derivative of VG over this phi S. Phi S is the surface potential. Surface potential. So this surface potential is the voltage at the surface of the silicon, which is related to the gate voltage. Gate voltage is something you apply to the gate. Let's say you have a transistor, right? This is the voltage you apply from the gate, but the surface potential is the voltage at the surface of the channel. So the voltage you apply from the gate may not 100% applied to the surface of the silicon. There's a voltage drop. There's a loss of the voltage due to the coupling from the gate and the channel capacitance. So let's say you apply 1 volt from your gate, maybe 0.7 volts really apply to the channel. Okay. And then the second term here is how this channel potential would impact the drain current. Okay, this is the second derivative. So if you decouple these two, then the first term is determined by this voltage divider effect, right? So you have this formula because here you have a CDM is a depletion capacitance, and COX is your gate oxide capacitance. So it's a voltage divider effect. So you can simply get this one, which is the phi s divided by Vg, right? Or the other way around. This Vg divided by phi s is the ratio of those two. The ratio of the, let's say, CDM over the total. You just apply the simple capacitor, in series kind of the rule, you will get this. So the second one is how the drain current would vary depending on the surface potential. So this is purely due to the Fermi direct statistics. So that's why you have KT over Q, and then here you have this factor. The reason is that here this natural log 10 is because here when you plot this scale, this is based on log 10. But in the Fermi function, it's exponential based on E, natural log E. So if you convert log 10 to log E, you have this conversion factor, which is about 2.3, this number. If you take a natural log 10, it's about 2.3. It's a constant value, okay, 2.3, just because of the change of this unit. And then KT over Q, this is a thermal voltage. KT is a thermal energy, depending on the temperature, okay? At room temperature, this KT over Q is about 26 millivolts. And then if you multiply by this, you will get roughly 60 millivolts per decade. That's why this is a fundamental limit. If you look at the Mosfet, no matter which Mosfet made by TSMC or Intel, no matter who, the best you can get is 6 millivolts per decade. And actually it will be more than that. The reason is that here, this is 60 millivolts per decade, but you have this factor in front. This is always larger than 1. It's 1 plus this ratio, right? This depends on how well the coupling is from the gate to the channel. The best you can do is 1, but in reality, you won't get 1. It's always larger than 1. So that's why the SS is always larger than 60 millivolts per decade. Today, the best transistor you can do is about like 65 or maybe 70, around that. So this is a fundamental limit by the physics. So this matters. Question?
I'm confused about what a decade is in terms of unit. Can you explain it?
A decade means 10 times
10 times of
current change. Yeah. So here, why this matters? This will limit your smallest, let's say, the threshold voltage, because your off current needs to be really off, right? So you consider the transistor is off. Then your current, let's say the current here, I off versus the I threshold, at this time. You want the I threshold divided by I off at least larger than 10 to the power 5. Okay. Otherwise, the off is not really off, right? You still have some leakage. So if your requirement is ITH over I off larger than 10 to the power 5, then that sets your minimal VT. What is the minimal VT? Can anyone tell me? What is a minimal threshold voltage? 300 millivolt, right? 5 times 60 millivolt per decade, right? You have 5 decades. So here, that's why transistor voltage scaling will not happen, because fundamentally, your threshold voltage cannot be scaled below 300 millivolts. Actually, 300 millivolts already is like the best case you can get, right? So any questions? So today's transistor threshold, 300 millivolts, 400 millivolts. And then your VDD, your power supply needs to be larger than that. That's why the lowest VDD you can get is about like 600 millivolts today. Okay. So let's continue. So here from the band diagram point of view, you can understand the short channel effect. So basically for the short channel, the drain is so close to the source. Therefore, the electrons can easily jump over. That means even at, let's say, at lower short channel, your off is not really off, right? This barrier height is reduced as you shrink the L. So that's why the leakage current will increase. And also, it will have a very strong VDS dependency. Because for the long channel, if you apply this VDS from 0 to VDD, then you will bend down the drain, but it will not affect the barrier height here. But for a short channel, if you push down the drain's voltage band, then the electrons can jump over. So that's why as you increase VDS, the I off will further increase for the short channel. So this is a fundamental challenge for scaling. Okay, so here then let's look at some real data. Let's say I on versus I off. So here this is from Intel's 45 to 32 nanometer transistor characteristics. And you have I on in terms of the milliamp per micrometer, and then I off nanoamp per micrometer. And this is in log scale, okay, for the I off. So at the same technology node, actually you will have different kinds of transistors with different VTH, okay. One is high performance transistor, HP, with no VT, and then low power transistor with standard VT or high VT. So with the scaling, you will push this envelope towards this direction. So you can view that, okay, with the scaling. Here, if your starting point is here, if you keep the same I off, your I on will increase by 14%, okay? And this means your circuit will be faster, right? Because in digital circuit, to the first order, the delay is C capacitance times VDD divided by the on-state current, right? So you want to increase on-state current. Or if you fix on current, then by scaling, you lower the off current. This is important to reduce the leakage power, because power has two components. The first one is standby leakage, which is I off times VDD. And then the second one is the dynamic power, depending on the clock frequency and the activity alpha. So the scaling always help, okay? And then for the VT tuning, this rely on this so-called work function engineering. So for today's transistor is all high-K metal gates. So here are the metal gate, here are the metal gates. You can choose different metals where you have different work function, like the Fermi level is different. Therefore, if you want to have for NMOS, if you want to lower the VT, you should choose some metals with, higher Fermi level. So this is a Fermi level with a vacuum. That is the work function by definition, with a vacuum level. So basically, by changing the gate metal material, you can tune the VTH. That's why on the same technology platform, you have different kinds of transistors available for circuit design, either high voltage, or either high performance or no power. Okay. Any questions? All right, so then let's continue with the CMOS scaling. So here, this is a historical trend that I gathered over the past like 20 or even 30 years. So here, you may often hear the tech node, like here, 180 nanometer, 130, 90, 65, 40, 28, and so on. So here, if you look at the year that this tech node was introduced to follow this scaling, right? Next Moore's law follows the scaling. But I have to emphasize this tech node, okay, does not mean anything, okay? In the old days, yes, above like 300 nanometer, even if you look at like 1970s, 1980s, then the tech node and the physical gate length correlate with each other. But since the 250 nanometer technology node, the gate length scaling actually speed up due to because at that time you can do some like a source and drain diffusion into the channel, and then you can make the physical gate length actually smaller than the patterning, than the layout gate length. So you see some deviation from the tech node. And then in the recent years, you see that the physical gate length actually does not really scale. Or you can say it stops scaling in today's like 5 nanometer, 3 nanometer. So for today's 5 nanometer, 3 nanometer gate length is still like a 15 nanometer, 16 nanometer, somewhere here. It's totally decoupled from the tech node. And here we have some milestone where the new technologies was introduced. Like at 130 nanometer copper interconnect was introduced. Previously for the interconnect routing is all aluminum. And then 130 nanometer copper was introduced. And then 90 nanometer strain silicon was introduced. And then 45 nanometer high-K metal gate was introduced. And 22 nanometer FinFET was introduced. So those are the key innovations. But here, the key message is that the tech node does not equal to the gate length. Tech node, I would say, is a marketing symbol right now, okay? It's a marketing stuff. When TSMC say like 3 nanometer, nothing is 3 nanometer on the chip. Okay, you cannot find anything. Or maybe the gate oxide thickness is like 3 nanometer. Yeah. Question?
Would you be able to correlate that to the resolution of lithography, or is that?
No, it's all totally uncorrelated. Okay, it's marketing symbol. Okay, to talk to the sales. Okay, they will tell you this is a 3 nanometer or 5 nanometer, whatever. So then, what is the really scaling? Okay, here it's not the physical gate length, rather this is a contact gate pitch and metal pitch. Okay, so what is this? So forget about the physical gate length. That does not scale anymore. Okay, but the scaling, as I said in the first lecture, Moore's law is still alive. The scaling still happen. Okay, but not the physical gate length. So what matters about the integration density? You need to look at the unit cell. For example, you take a look at the standard cell, like an inverter or NAND gate, NOR gate, whatever. The standard cell, it always organized. For example, you have the NMOS region, PMOS region, and then for today's FinFET design, you have those fins, the green fins. Okay, what matters is, let's say, for this area, you want this area to scale instead of the gate length. So what matters for this area? Okay, so for the standard cell, what matters is this contact poly pitch or contact gate pitch. This is like a source to drain, the middle of the source contact to the middle of the drain contact. That is the contact poly pitch. It's called poly because the gate used to be polysilicon, but nowadays as we switch to metal gate, so sometimes people call contact gate pitch is the same thing. CPP equals to CGP. So that is the horizontal dimensions indicator. Okay, and then vertically you care about the cell height of the standard cell, and then that depends on how many metal track you are going to use for the routing. So here then the metal pitch, this is M1 metal pitch, is the indicator of the vertical dimension. And then of course for the standard cell, you will ask how many metal track you use. But anyway, so if you look at these indicators, like the CGP and metal 1 pitch, M1 pitch, it scales to today's like 5 nanometer, especially the metal 1 pitch keeps scaling. And then the CGP slows down a little bit, but still they scale, at least to 5 nanometer or 3 nanometer today. Moving forward, it will slow down. And here we have those numbers. For example, at 5 nanometer, G48, that means the contact gate pitch is 48 nanometer, roughly speaking. Different foundries may vary a little bit. And the metal 1 pitch is like 30 nanometer. So this is how we define the integration density. What matters is those dimensions. Okay. Question? M30 is the metal 1 pitch is 30 nanometer. L1, this means 1 layer, 2D design. L2 means we are going to move to the 3D CFET or multiple NMOS on top of PMOS, multiple transistors vertically stacked. L1 means still only 1 layer of transistors. Of course, those are the projections. This will be seen in a few years.
Does this scheming also show the transition from FinFET to gate-all-around?
Yeah, so gate-all-around maybe somewhere here. Yeah, but then we will talk about gate-all-around. But then from the layout point of view, you don't see the difference, right? Your gate all around nanosheet transistor will still look like a fin, like here, right? But here the dimensions like a gate poly pitch, the contact poly pitch, and then the metal one pitch, from the layout point of view, will remain the definition. Of course, you will scale that based on the design rule. Okay. So let's look at this design rule. Again, so this is from the planar transistor. So if those two transistors are isolated, then you have some like isolation in between. But in many cases, those transistors will, connect with each other. And then the contact gate pitch is defined here. This is a CPP or CGP as we discussed. The center of the source contact via to the center or the middle of the drain contact via. So here, if you still use F, like the gate length, then in total, you will get this kind of dimensions depending on the design rule. How many, F you may need between those spacings. So let's take a look at the NAND logic gate, 2-input NAND. In the planar, okay, technology node, then this is how it look like, right? So here you have two NMOS, and in between you don't need the contact. They are in series, those two NMOS. And here you have two PMOS, they are in parallel, so you need to add this contact in between. So here you see that this is the contact pitch we talk about. That's why here you need two contact pitch for this PMOS region. So any questions? All right, so then let's look at the definitions again. As I said, the key indicators here is the CPP or CGP and the M1 pitch. This defines the logic transistor cell area, right? Instead of the physical gate length. So different foundries will define this differently. That's why here I say this is the market symbol, right? TSMC 16 nanometer, this is the design rule. Like CPP 19 nanometer, Metal 1 64 nanometer. And then 10 nanometer and 7 nanometer definition. Of course, it shrink. But different companies will name differently. So here, Intel's definition, 14 and 10 nanometer. Actually, at that time, it's more closer to the, Intel's 14 is more like TSMC's 10, and Intel's 10 is more like TSMC's 7. So that's why at that time, Intel criticized TSMC is cheating. But then soon, TSMC is leading in the technology development, and Intel has to rename, right? So this now become Intel 7. If you look at this become Intel 7. So any questions? Okay, so moving forward, the CPP scaling will saturate, okay, and then the metal one pitch and also fin pitch scaling will also slow down, but still the transistor density will increase. The reason is that the cell height, the total height, will reduce by reducing the number of metal track and also the number of fins for the NMOS and PMOS region. So here M1 pitch is only this, but how many metal one you may use for one standard cell? Let's say for one inverter or one NAND gate, NOR gate, how many of the metal track you use could be reduced as we scale down. So here the very important concept is called fin depopulation in the recent technology nodes. That's why you can enable the 6-track or even 5-track design. So here the idea is that, okay, previously in the 14-nanometer node, for the NMOS, you need a 3-fin for the NMOS and 3-fin for the PMOS. So here you have 3-fin for the NMOS, 3-fin for the PMOS. Because each fin is going to give you certain amount of current, okay? But for the standard cell design, you need to satisfy certain timing requirements. So you need certain amount of current. If each fin can give you more current, then you don't need so many fins. This happens, okay, for 5-nanometer or let's say today's 3-nanometer, you only need 2 fins or even 1 fin to give you enough current. The reason is that as we talk about the FinFET technology node, each fin will give you more current. So previously, maybe the fin look like this, okay? And then in 5-nanometer, it may look like this. Each fin, because the current conducts along the sidewall of the fin. So each fin will give you more current. So that's why you don't need so many fins to complete your standard cell design. This is how you reduce the standard cell height. This is a key driver to maintain the Morse node right now. Because this dimension, I mean, does not really scale too much. What matters is here, this one. So any questions here? You understand what is really scaling here? Okay, so then let's move on to the memory. So memory people are more honest, I would say, okay? So the memory's pitch, really the F, memory, you can really talk about the F, because the DRAM F is defined really as the metal 1 pitch, half of that, okay? Metal 1, let's say for the bit 9 to bit 9, like routing, then you have the metal wire and then the spacing. So half of that is defined as the F, okay? Also for the 2D NAND, from the poly to poly, because you have the transistors in series, this gate to gate poly pitch, and half of that is F. So those are really driven by the lithography like resolution. So this is like F. Let's say pitch is half pitch is F. And in 3D NAND, it's hard to define, but you can think it's from the pinner to pinner pitch, half of that. But in 3D NAND, we do not really talk about the F, because what matters is how many layers you stack. Okay. Actually, the F in the 3D NAND, if you use a pinner pitch, this is much larger than the 2D NAND. So any questions here? So for logic, to answer your question, the F lose the meaning, because if you assume the F is still the tech node, then this does not really correlate with the density. So for the logic, what you want to use is this CPP and metal 1 pitch, and then how many metals for the standard cell. So those are the key indicators, okay? For the memory, DRAM and 2D NAND, you can still use F as defined here. For 3D NAND, yes, you can define the F like this way, but then what matters is how many layers you stack, okay? Any questions? So you can loosely use F, but you have to normalize that. So what matters is the real absolute value, micrometer square. Of course, you can artificially divided by the f. If you assume f is 7 nanometer, you can normalize to that, but it's just a number that you normalize to. What matters is the real silicon space, right? Yeah, you have the VDD and VSS routing, so that will also, use some space. That's why the backside power delivery is proposed, because you don't want to you don't want to spend space for the VDD and VSS routing here. So the standard cell, includes the VDD and VSS routing. So you want to hide those VDD VSS to the backside of the silicon. This will happen in 2 nanometer and 1 nanometer load. Yes. If I recall, used to be like 100 nanometer, 120 nanometer. I don't know if they scale below 100 nano. So on that order, maybe 90 nanometer, 100 nanometer, around that. So use the use the smaller ones. Okay. All right. So then here is a quick summary, right? So here are some key innovations in the logic scaling. As I said, so 90 nanometer, the string silicon was introduced to boost the mobility. And string silicon means you're going to use maybe silicon germanium as a source drain instead of pure silicon to have some stress to the channel that will change the crystal structure and then the mobility. And then 45 nanometer high-k metal gate was introduced to solve the gate leakage issue. And then FinFET was introduced 22 nanometer to really combat with the short channel effect. And then 3 nanometer and beyond, then we will do this stack nanosheet. And actually, Samsung already announced stack nanosheet, but Samsung call it gate-all-around multi-bridge channel. Basically this thing, okay? Different companies will have different name. Intel will call it nano ribbon, and TSMC, I don't know, maybe nanosheet. So Intel and TSMC will also plan to transition to the nanosheet from the 2 nanometer or maybe 18 angstrom nodes. So that will happen very soon. And then what comes after? Okay, this one. Then the industry already has a roadmap for 5 angstrom node. So that is here. This is from the Intel's paper, 2020 IEDM. So we used to have NMOS and PMOS, right? Remember the standard cell. The top part is the PMOS, bottom part is NMOS. So you occupy the natural space. So in the future, they want to do the stack CMOS or CFET. They call complementary FET. So that means here, for example, NMOS stack on top of the PMOS, NP. And here are some early demonstrations. You see NMOS stack on top of PMOS. This is ultimate like logic scaling. As far as we can see today, okay, this may happen in 7 years, 8 years from now. But this is what industry can see today, okay? So if you look at the stack nanosheet, we are entering this atomic world because the dimensions, the nanosheet are a few nanometer, maybe it's 2 or 3, 3 or 4 nanometer. Then the atoms, you can count the atoms in that scale. So there's not too much room left. Yeah. But at least I think in the next 5 to 10 years, the logic scaling will happen until we reach this CFET. And then after that, we don't know what will happen. Of course, you can do the heterogeneous 3D stacking bonding, chip to chip. But then for the front end, CMOS, we don't have solution after that. This will happen maybe after 10 years, maybe. All right, so I think that's pretty much what I want to share today. So any questions before we end? All right, then I'll see you next Tuesday.
I think at this point, right?